So we've been talking a lot about differential equations of this form here, most recently in the context of modeling the memory potential of a neuron, and more accurately we've been talking about neurons that have a passive membrane, that is, they don't have active ion channels that are opening and closing, and thereby influencing the membrane potential. So for this simple system, I derived this solution in a previous video. So this solution describes how the membrane potential of a neuron, or passive membrane, would evolve over time. And that is true, but in that video I made one very critical assumption, and that assumption was that the steady state voltage, as well as the time constant, did not change over time. And in the last couple videos, I have we've begun to see that that assumption doesn't always hold. And specifically, we've talked about the situation where you might have some cell, and you can impale the cell with a glass micropipette electrode and pass current directly into the cell through this electrode. And that would change the steady state voltage by the following equation. So the steady state voltage would be equal to the resting potential of the cell, which I've been denoting as E, plus the input resistance of the cell times the amount of injected current, which I've been calling I and J. So I and J is being injected through this through this electrode. So the next question to ask is, well, if we have this capability of controlling the memory potential of cells, what kind of current inputs would we like to use? And I gave the example in the previous video of a simple step current, where you essentially just switch at some time point, you turn on the electrode and you begin to inject current, and then at some other point you turn off that current injection. And this was nice, it was simple, and it gave you the intuition of, well, a membrane with a capacitance is going to respond to this by slowly exponentially rising to steady state, and then once it's turned off, it'll exponentially fall back to steady state, and you sort of get this rounded pattern. So that's nice, but what happens if we have a more complicated input? So, for example, in actual biological systems, neurons receive many simultaneous synaptic inputs from hundreds or thousands or even more presynaptic partners. And if you think about it, not all these partners are going to be having a synchronous input or a synchronous effect on the cell, so you might get something that looks like this and has a bunch of noise. So this current profile might actually be something that is more representative of a neuron would actually see in a naturalistic setting. And this input that I've drawn here is just horribly complicated, and there's no way that, or you might think that there's no way that we can analytically solve for what a passive membrane, how a passive membrane would respond to such a perturbation. So in this video, I'm going to show you one way of figuring out how a passive membrane would react to such a stimulus, and then in a future video I'll show you a different way. In this video I want to specifically talk about a numerical method for solving this differential equation up here. And for those of you who aren't familiar with the term numerical methods or numerical solutions to differential equations, I'm going to post a couple of references and videos in the description of this video. And I suggest that you look at those first, because if you have an understanding of, sort of the basics of numerical methods, the rest of this video will make a whole lot more sense. It's not that it's super complicated, it's nice to have a little bit of background before diving into something. So very briefly, the idea behind a numerical method, we'll have some time-dependent function, so we'll say we have a dynamical variable x, which is a function of time. And if I know the initial condition of x, which we'll call x0, then we can solve for, or approximate, the full function of x by solving for the derivative at time 0, which I'll denote as x dot. And then, because we know the derivative, we can assume, or we can approximate, the behavior of x in the neighborhood of this point by using the first derivative, and say, okay, in the next point it's just going to be somewhat in this area. And then on the next point, we again calculate the first derivative and then move to the next step. And this incremental process that I'm describing here is known as a forward Euler technique, or Euler's method. And if you do this iterative process again and again and again, then you can sort of sketch out what this time-dependent, or this function of time, actually is doing. So I will, again, post some references to this if this explanation is sort of going a little too fast for you. But what I want you to notice in this example is that all we're going to do is figure out if we know x at any given point, we can estimate x at some point in the near future of x, and then iteratively solve for the future points of x. So moving back to membrane potential now, what we want is a way of estimating the membrane potential at some time point, n plus 1, based on the voltage at the previous time point, which we'll call voltage, or Vn. And what you can realize by looking at this solution here, which again assumes that the steady-state voltage is constant, we can extend this solution and use it as a numerical method to solve for the full function of membrane potential over time. And specifically, all we need to do is input the voltage at any given time, n, into this equation here, and sort of use this as our initial condition, and then say, in the near future, the voltage is going to evolve according to this equation. And the reason that is actually a good assumption, or a good approximation, is that both the steady-state voltage and the time constant are probably not going to be changing very quickly. So, for example, if you input a sinusoidal current into a cell, so if this is my I injected, so I as a function of time, then so the steady-state voltage is going to be changing on this time scale. So let's say this frequency here is on the order of, I don't know, like 0.1 seconds. Then if we take a small time step and just look at any small window of this function, the steady-state voltage is roughly going to be constant. So if our time step, delta t was 0.01 seconds, then the steady-state voltage is going to be relatively constant, at least in that time window. So I'm just going to write this out for you quickly, and then hopefully it'll make more sense when it's all written down. So this is sort of the algorithm, or the basis of the numerical method I want to present. Essentially, you can calculate the voltage at a time step in the near future based on the current voltage, and based on your estimation of the steady-state voltage also at your current time point. So V of n corresponds to the voltage at time equals n, let's say, or actually n delta t to be precise. And you can see that delta t is now has now replaced t in the previous equation, simply because we're iterating in small steps, small time steps, and those small time steps, we're just projecting that much forward into the future. So you can think of it as being as v of n being your new initial condition, and then once you have that initial condition, you're going out a small amount of time and projecting and estimating the voltage into the future. So again, the basic assumption here is that the steady-state voltage is going to be roughly constant if we make delta t very small, and if the steady-state voltage is changing very rapidly, then we will need to make our time step smaller. But if we go down to the limit of delta t approaching 0, this will work very, very nicely. So that's pretty much it for this video. I might post some code to actually show you how this works in action. And yeah, so I guess the last question that you might have is, why use this this method here when there are so many other numerical methods? Like you could use forward Euler, which I alluded to earlier, or a Runge-Kutta, or some other sort of more standard numerical procedure. And the reason is that by using this numerical method, you are taking advantage of the special form that the differential equation has. So this is a very accurate and a very efficient way of doing these simulations, and it has other sort of nice properties of dealing with stiffness in differential equations that I won't really get into. But this is a very nice numerical method, and I use it myself. So, and it's also nice because it directly falls out of sort of an elementary analysis of these sort of systems. So I hope that you sort of understand this, and if you don't, I'll post some code, and hopefully that will sort of clear up exactly how you can utilize this approach to solve for the membrane potential when the steady-state voltage is manipulated by some current impulse. Thanks, and I will see you in the next video.